Alright. A little bit about me. Hello, I'm Stefan. I founded the Rust Zürisee in 2017, and we did that mainly to organize Rustfest. Rustfest is currently in hibernation. I'll say it's a little bit complicated, but there is a Rust conference called Eurorust, which is similar and will be in
October
in Brussels. So if you want to go there, Eurorust, it's nice. This talk is my master thesis, so I will indulge a little bit more because we're not that time restricted. But yeah, it won't be too long. So for my record, 1956, and you have to remind me to take a note of the time when we're done, so I know how much I can compress it for the defense. So, why encrypt in the application? Like, there's a lot of cryptography, there's a lot of systems that work. We have Lux on Linux, we have BitLocker on Windows, we have Apple's thing, got what it's called. Yeah. Android uses X4 file encryption, works as well. Why do we need another one? Well, the trouble is, how do we manage it, right? How do we manage it independent from the operating system? Or how do we deal with the fact that people maybe switch their phone or lose it? And for the developers, how hard is it to use BitLocker correctly? Like, how many group policies do you need to enable it fully? I guess it's at least a 2-digit number. So, a lot of fun. Also, the backup. A lot of the systems, especially the Google ones, they don't consider backup. They just sync to the cloud. So, what kind of security guarantees do we need? Can we stop offline attackers? It's like the first time. Someone steals my device, and I'm lucky it's powered off. Can we prevent that? The answer is yes. What if someone with 3-digit letters something does something to my hardware? Manipulates the firmware. Can I trust the device? Nope, it's gone. What if someone installs new software, like on the phone? I have to trust Google or Apple or whoever manufactures that. They can change the operating system. They can also inject code into any application I install. And actually it's a feature now. If you notice the Google feed, they have a new feature since last spring, I think, where they compress the applications depending on the end device. So Google know this device is that specific configuration, so they throw out all the things that your application doesn't need, repackage it, they can do whatever. We can protect them. So, same with 0 days. It's basically as soon as someone has the hardware, like before, they're done. Is it a debugger? Yeah, sure. Is it something else? If we encrypt the memory, our application still needs to use that, right? We still need to have the master key some time. Maybe it's protected some of the time, but we need to get access to it once we need it. So an attacker can just wait, and then they get it. So it's just obfuscation. It's annoying. We can piss off attackers. It might be fun, but yeah. So what technology? I don't know. So memory safety is really nice. Oh. It's the wine. I'm very proud of this forbid unsafe code. Because in the beginning I was like, I'm implementing a file system basically, so I guess I need to cheat sometime. But turns out we can do that in a safe way. Maybe a little bit slower, but it's safe. Then we can upgrade all the software we use. So we can exchange SHA, with Argon 2. We can replace AES with SHA-20. And we don't have to sift through the endless amounts of IS modes. We can just use poly 1305, and then we have the signature included in one step. Very nice. The professor that is running the institute I'm with has a project called DigiDo. Quick sidebar. It is an identity manager, and they have the stance that they're like, okay, facial recognition technology is coming. We can't prevent it. There's lots of bad actors. So they want to offer an alternative and say, okay, you want these meme features? Okay, here's a way that's less intrusive than just scan the whole planet and then make a database of every face on the planet. So if you're into building security, DigiDo is a thing where when you walk up to a building, your device goes to the company and says, okay, my user is in front of building 15, now upload the facial scan, and then the building will recognize you while you're there. When you're at home, your phone is like, I don't know where the user is, so the building won't recognize you. It's also nice if someone hacks the building. If they just hack one building, they have the facial data of the people that are at that time near that building or inside it. Everyone else is just like, ooh. All right. Should I elaborate why I want to replace AES now?
Yeah.
That's a little dicey. So, there are two papers I've read. One is actually quite old. It's from 2005, and it's from Bernstein. And he noticed that if AES is not accelerated in hardware, then it relies on memory movement, which relies on cache lines. And then we notice latency differences between in register, L1, L2, L3, and memory. And with these differences, we can extract the key. It's been known since 2005, has been fixed mostly by running it in hardware. Until last year, where people noticed that with the latest microcode updates, there is timing differences depending on the key and the input. So, yeah. IS is fine over the network, but if you have a shared virtual host, it may be tricky. Another thing is, it works with S boxes, and honestly, that's the ping of AES, the part of AES I do not fully understand. I can read it, and then I'm like, sure. So, why not have XOR, integer addition, shift with roll, and that's all the things I know. It's still a little bit magical, but yeah, it works better. I can follow that more. So what about speed? We have, in every device since at least 2010, we have a hardware accelerated AES. How does it compare? We're lucky. So on the left, the first two chips don't have hardware acceleration. The last one has. So back in the day, this was from 2008, I think. It was half the speed, but it's still half a gigabit. And that's fine. Without any hardware acceleration, and we're way faster on devices that don't have it. Granted, that case has gone. Every device has AES nowadays. But if we phase out AES over the next 20 years, maybe we'll just reallocate that silicon for something else. It doesn't matter. There's a good chance that the modern accelerators will be more FPGA-like. We can reconfigure them at some point, or your firmware can configure them. So we'll see what the future brings. But at least for SHA-20, speed is not the issue, because it's XOR, adds, and shift rotation. So we're good. CPUs can do that very well. We made it through the first part. Okay, brace yourself. Now there's the crypto. You ready? Okay. So I would like to keep the master key in one place. That's not possible, sadly, but I can keep it in as few places as possible. Then I need to update the nonce, the number used once. So I can use the type system of Rust to update that automatically. Who here knows about the drop trait? Half the room, a little more? Who knows about this structure from other languages? Okay, so it's basically the same, except you cannot call the drop as a function call. It's a language feature, and the drop function that's in the standard library is literally an empty function that just absorbs the object into a scope. End of scope runs the function, and then we can have references, update nonces, call other functions, automatically flush all the things to the disk. Since the device that will be running the software is most likely to be somewhat networked, I will lock all the things. So this is traditional file lock, and there's a new thing called the Rustix. Anyone heard of that one? So the Unix part. Who has heard of Moozle? A couple. Okay. libc? Even more. Okay. Rustix is an abstract libc-like library that just implements all the system call build-ups in Rust. It's very promising, and it's very fast. It's very nice to compile because we have full types. So it's not like the libc crate where we just have an orgy of constants. And if you want to do something with the file, you have to know, okay, I can use these 50 constants, but not the 500 other ones. So Rustix makes that very nice. And the autosave already told you that's the drop crate. You can implement the trait for all your types. So, as I promised, the math. In the first part we have green and yellow. Green is what we generate when we start a new share, folder, volume, whatever. And yellow is the user input. I calculated that we need 42 characters of user input. It should be very random. Or something equivalent. So if we want to have something that people can remember, like a big sentence or a selection of, I don't know, a couple words, then this needs to be longer because the entropy depends on the input. We need 32 bytes of input, 256 bits. That's the entropy strength we would like to have. If we use something longer, we can, like paper keys, right? They're not that strong, but they're long. Now, we generate the key slot by using Argon 2. And what Argon does, it takes our input and just stretches it. So, of the 256-bit minimum input length, we generate twice as much. If our input is longer, because we use a less sophisticated scheme, let's say we only use the digits, just 0 to 9. We need a very longer input than 42 numbers. But we can still use the same function, and it will generate a key that upholds the same guarantee that it has this strength of 256 bit. Once we have that, we slice it into 3 parts. I'm sure you cannot read it, so it's just 1, 2, 3. We XOR the first 2 slices with the generated keys and store that. And the last slice is our check value. Because how do you know when you decrypt something that's supposed to be random that you decrypted the right thing? And the check value is not encrypted, but you can only get the correct check value if you have the correct input. And then this all flows through. Down here in blue, it's all the things we store. With me so far? Yes. How do we reverse that? So, in blue again, what we have stored, user input. We do the same thing. We take the input, we generate our key stream. The salt is also stored, so we can just use that. And then we have the check value from before, this last slice. If it's wrong, we just don't use that key. We loop through all the keys. If we can't find any, user doesn't know the input password, or any of the input passwords. If we find one, hooray, we can XOR, and then we have the master key back. I think that's really neat. It took me 3 attempts and 3/4 of a year to come up with this scheme. Yeah, that's it. Questions? So I validated this, by the way, by asking Filip Jovanovic. He used to be with my professor, but now he's his own professor in University College in London, and he said, looks good. So, yeah.
How will you call your file system?
It has a very sexy name. It's very long. No, I called it Encrypted FileSystem Storage. Yeah, I'm not the marketing department. There's another thing we need to do. We have these nonces that we keep updating all the time. The master key nonce is used for the index file. Every time we touch that, we need to update that nonce. Every time we add a file, remove a file, maybe it shrinks, or we change any of the attributes, we need to update that nonce. We don't have the other keys. We just have this one key that the user or the TPM or the hardware security module gave us, and we have the new nonce. And funny story, we don't even need to keep that around, because we just have the old nonce when we decrypted it, and we have the new one, which is usually just +1. And then we can loop through the stored keys, including our own. We don't need to know which one is our key. We XOR the slot nonce, so we have the temporary value, and then XOR it back with a new value, and store it back. That's really neat. Don't need to carry all the keys all the time. And now, you've earned it. These are some flowers, took the picture this afternoon. Isn't that nice?
One question maybe?
Yes.
If I can, how did you compute the input length?
The input length for the minimum of the 42.
Yes.
It's a very complicated procedure called Dreisatz. So we have 8 bits in a byte, but roughly 6 point something, let's say 6, that we can actually input with ASCII. So it's just 256 divided by 6 multiplied by 8. No magic. Good question though. So, now we can use it. Now we have our key management solved. Okay, now we actually need to store the files. And yeah, Bernstein is on a lot of my things. He did most of the crypto I use. And there's the ring crate. It's okay. It's clearly done by people that do a lot of math and not a lot of programming, but it works. It's reliable, and the docs are reasonable. So, it has C and assembly code from boring SSL. Anyone know that one?
So it's not safe.
Well, Google considered it safe enough. Is that a good argument?
Google considers Chrome good enough, safe enough, right?
Yeah, it's a bad argument.
That's because it comes from these.
They forked OpenSSL, which is A+ in code quality, as we all know. I think the last really bad exploit happened 2 weeks ago. So, yeah. But, and here's the thing, we don't use a whole lot of OpenSSL or boring at that point. We only use the very tried and true modern parts. And most of the exploits come down to weird parsers that for some reason people still insist in writing in C and all that algorithms. I mean, if you exploit MD4, are you really that brutal of a hacker? So, how can we do this? Let's go through it quick. Hash map, easy. Left half is the path. Thank you. And the right hand is stored info. So, what do I mean by that? When we load up the storage, it could contain hundreds of megabytes of stuff. We don't want to touch that until we have to. So we just load the index and do nothing. Until someone requests access to a thing, and we can check if it exists, we can load it. The size that is reported is wrong. AEAD has padding for the block cipher, and then a tag. So we could say, okay, on average, we're at about 12 bytes too long. It's not too bad, but if you really base your algorithm on file size, you actually have to load it from this to know how long the file actually is. But is that really the use case? Because this is intended for storing your picture, maybe a facial fingerprint, your driver's license. So not stuff that we need to know the exact length of. So should be fine. And of course, every file that's open, the backing storage is all locked. So if we have the directory on a share, which is a thing you can do with the system, but you don't need to have something like syncthing or rsync or whatever to translate. Oh, thank you. Thank you very much. We lock it. If the share supports file locking, so Samba, NFS, we're good. We can have multiple instances running on the same thing. They just lock, and since it's lock exclusive, we can guarantee that what we read back is actually in the store. So there's no read-write lock over multiple instances. Makes design way easier. Yeah, profile loading on demand. And of course, since we have the drop, we can automatically release the file info once we don't need it anymore. So before we get into the native integration, I'd like to say a little thing about how to handle files. In the beginning I was like, yeah, okay, let's just use a pointer or an arc. Anyone know arcs? So it's atomic reference counting for the others. It's the thing that the JVM does by default. It makes it a little hard, because then it's read-only. So we need a mutex. So now we have a mutex per open file. Ah, that's annoying. So, I moved all the mutexes up into the CryptoFS structure. So, I hope this is readable. This is a generated view of all the structs that are in the crate. Everything in blue is from the standard library. Everything in gray and red font is from my library. Everything black and white is from something else. Yeah. You see, there's not much else. And of course, there is a bug because it doesn't recognize these types correctly, but it's good enough. So what we do is, CryptoFS has a mutex, arc, and then the mutex is over there. That goes to the live keys, and then if there is an open file, we get access to the actual file. This arrow, oops, sorry, this arrow down here, file. This is my own file structure. All it does is lock the file. And on the other hand, we have a secure file handler, and This is also reference counted, also atomic, but who knows weak? Nice, 2, 3 people, 4, yes. So, what's the problem with reference counting objects? Like the garbage collection problem, if you have reference counting everywhere.
Circular.
Yes, circles. Weak solves that problem. With weak, we can tell this is a strong reference versus this is a weak reference. So, all we have to do is check the secure file handler with every access. Is our main crypto BFS still there? If not, throw an error. If yes, continue. That's all there is. The Rust guarantees that the backing memory will be around for as long as needed, but the drop will have been called. So you cannot touch the memory and expect something reasonable from that. It's sound. Also standard library. This magical key ID that's running around, it's basically hiding a uint, a U64 int. And that's the beauty of this indirection as well. I have to talk to Android, which we'll talk about soon. So I don't have to copy a pointer and care, ooh, okay, I have to somehow hide the implementation and move memory back and forth. No, I just copy this int, and that's the tag. It will be different from every run. It starts at 1, I think, or at 0. Just goes up. Every time you open a file, goes up and up and up, passing back and forth an int. Super easy. So, very nice for FFI. All right. Back to the beauty slides. So, native integration. That's the really big thing for the digital project. And the biggest one is mobile devices, especially Android, so let's get into that. How do we do that? We have a build system, it's called Gradle. It was supposed to replace Maven, it somehow still uses Maven. I don't know. Okay, we need a native toolchain. Rust can bring that. Okay, we already have some cross-compile toolchain in Android Studio. It's called CMake. CMake is independent. Comes from C and C++. Very powerful. And then we have the Kotlin runtime. We need that for all the interactive stuff. So permissions and dear user, the application wants to store files. Where do you want it? Because in the latest 2 Androids, you as the user can choose where you store the data. Okay. Also access to the fingerprint reader or facial ID or whatever your device supports. All Java or Kotlin interfaces. So we have to use that. Who has worked with Android and knows how this will end? Will it end, yay, it just worked, or I see the horror. Okay, so Android is a very big system and it does stuff. Sometimes it works, sometimes the docs are right, sometimes the docs just don't exist. Yeah. So what are the major problems that hit me? Anyone want to guess? Okay, let's go on. So, I started the project in summer, the Android project. And then I did it, and had a working prototype in December. On Friday last week, I opened Android Studio and was like, hey, you need to update. Now the project is broken. Cool, okay. I start a new default project, just nothing in it. Literally empty activity, enter the name, run. Build fails. Yeah, because some part of Android decided that it needs Gradle 7.6. If you do that manually in the files, which you can't do to be fair, but you have to know that Google decided in their infinite wisdom that non-patch versions don't have the .0 at the end. Why? I mean, why? Everything else is 3 numbers separated by 2 dots, but the first one not. Okay. If you stumble over the UI long enough, then at some point you will find there is a drop-down menu that lists all the things in the correct values. But yeah, now I saved you a day of Google. You're welcome. Another thing is the fingerprint sensor. There's a very nice tutorial on how to verify that the user is present. And it's very nice. It's like, yeah, here's a snippet, here's a snippet. They're not consistent because that's too easy. But you can see, okay, that's the thing, it works. There's also method calls that you can put any smallish value into the hardware security module and get it out. But there's no examples, and I'm not an expert on Android, so it doesn't work. And of course, they are like, oh yeah, Kotlin, this is really nice, and it fixes all the problems of Java. But how do you generate the headers for cross-compilation for FFI? The answer is you don't, because the Kotlin team has not, I can't say that, yeah. You haven't come around to writing that tool. And the Java H tool has been discontinued, and the Java C.H prompt is only for Java code, because it's part of the Java compiler. So the easiest way is just compile, see the error message, and go from there. Let the linker guide you. Works surprisingly well. Other fun side note, look for the little ones in the function name, because sometimes they insert the ones. I don't know what they mean, but they're there. Especially if you pass more than one string, suddenly ones start appearing in your function name. Don't know why. Another thing is CMake is very, very plugin friendly, to the point where Android Studio has a compile commands.json for every architecture variant that you could encounter on any Android thingy. So if you want to just tell CMake, hey, here's my finished compiled library, just link with it, it will fail. You cannot find it. I haven't worked around that one. So another thing is the glue crate, it needs the cross-compilation toolchain. So you can go the Ubuntu route where just install every toolchain in your main system. Sort of works. Or you can use the SDK toolchain. But that doesn't work because for some reason the AR, so the archive repackage binary, is called differently depending on the architecture. And it's just called llvm-AR. Yeah. So you can fix that with a lot of symlinks, which I did, still didn't work. And then I found cargo NDK, and the auto detection is very broken, but you can get it to work. So this is the state. I have compiled all the things, now I need to link them. So that's easy, right? Experienced C++ programmers? Linking easy? Yay or nay? Oh, I see the horror. And we have 2 more platforms to go. But I guess these are easy because you can just use proper Rust code and don't do any weird stuff. Another fun side note is you can use virtual TPMs now. Microsoft offers that in their cloud. I mean, it's their cloud, it's their hardware, it's their TPM. I don't know. I guess you can convince a lawyer that this is more secure than nothing, but yeah. We made it! Isn't that nice? It's the Zürisee. It's like over an hour from here. Very nice. There's a waterfall which we cannot see in this picture. You should go there, it's free, just walk up there. Very nice. And that's it. Any questions? Oh yes, the time. Thank you. It's 20:31, so 36 minutes, so 35. Nice.
Actually, do I have a question?
Yes,
But
there you go. I think there's a second mic somewhere.
Yeah.
It's coming, but just give him the mic.
What did you use to generate a nice graph of your structure? Like the, you like kind of like the class diagram. Yeah.
This one. I wrote a Python script.
Okay, that's all.
Initially, I wanted to use the symbol crate from the Rust compiler, so, and the Lexer and whatnot. And then it turns out you need to have nightly and da-da-da-da. And then I realized I don't need complex answers, and if you use cargo format, your code is very easy to parse. Like all the weird edge cases are just gone. And then you only have to deal with like 5 different cases, like public, create public, private, and lifetime or no lifetime. And then, yeah. The Python script generates graphics graph, which is then just handed over to dot, which makes this PNG. It's not great for zooming in, but for an overview, it's good enough.
You have another question here?
Yes, please.
So 2 questions. Rust, total beginner here. Number 1 is you devoted a bit of time explaining how you would try to protect your secrets in memory. And in C, on Unix system, you use unlock to ask the system, please don't swap this region out to some other storage. Keep it where it is. Is that something easy to do in Rust? Question 2, you explain how the master key scheme works. Is anyone considering trying to formalize it to run it through Progerif or some other formal verification system?
So the second one is easy to answer, not me.
No, you don't have someone else.
There is a chance that another master student or a grad student will be tasked with that. I say there is a chance. There are currently no plans. It uses a similar scheme than Lux uses, Lux 2 actually, version 2, not 1. But this one is not limited to 8 keys, which is nice. So we can just add keys as long as we have storage. The first question, how do we protect it in memory? So that's an operating system dependent question. On Linux we can try to mark it. It's not guaranteed. On Android we can't. On macOS we can't. On Windows we can, but the operating system can lie. So I did not bother to do that. If someone tries to reverse engineer the binary, I mean, it's weird, it's open source, but they could. You would probably find the memory location at some point. Because the pattern is really easy, right? It's guarded between an arc and a mutex, and then it's just the first field. So, yeah, when you can attach a debugger to the process, it's over. Yeah. That's it. Sorry. I forgot to include the reference to PhD thesis of one of my colleagues that does try to prove that you can hide something, and in the process he made a proof that you can't. And it just boils down to the thing. At some point you have a legitimate access path to the thing, and then you can construct that access path. Yes, another question.
did you measure performance of your file writes?
Not yet, but the tests are like within a second done, so for small files it's good enough. And also I haven't turned on release mode yet, so oh yeah, for all the new Rust people. So when you say cargo run or test or something, default is it compiles your binary with all the debug information. The target binary even includes the source code of your project, like all of it. It's very nice for debugging. You can attach any here for your debuggers. You can step through. You cannot step back yet, although you can repeat the stack frame, so you can restart functions. So, very nice. When we turn that off and go into release mode, we turn on optimization, throw away all the things we don't need. We usually gain a speed up of a factor of 20, sometimes up to 400. And if you do anything with graphics, for instance, like a game or screensaver or something, it's very hard to develop that in debug mode, so you just develop in release mode. The link time goes up quite a bit, but the speed as well. And once you're done with development, you can turn on link time optimization and stripping. So we can enable another layer of optimization, and with stripping we take out all the symbols that are not accessed or visible, and then the binary becomes small and fast. So I had another application, it's a memory collecting thingy. When you run it in debug mode, the binary is almost 50 megabytes in size. And it just collects some stats and does some things, and then outputs a Prometheus text file. When we enable all the optimization, the binary goes down to 1.8 megabyte, and it runs in 0 milliseconds, so I cannot time that anymore. So, yeah. So speed up, there will be a speed up. I have measured.